Well, my little girl's getting Terrific Kid on Friday. Do y'all know what Terrific Kid is? It's like a thing, one of the insurance agencies or something, I think, in the state funds it, and they give them a t-shirt. It's sort of like Student of the Month, but it's like Student of the 9 weeks. So it's a pretty big deal. Did y'all ever get Terrific Kid? What's that, Courtney?
I got Student of the Month.
Oh, good job. Yeah, it's similar to that. So we should do a Terrific Kid in this. I mean, y'all aren't kids, of course, but do a terrific, I don't know, terrific adult. Yeah. Let's see here. All right, so we have two types of collisions, elastic and inelastic. In elastic collisions, momentum and energy are conserved. This is when objects bounce off of one another or they collide with one another, and there's no energy lost. Okay. In all collisions, the momentum is conserved, but only in a few collisions is the energy conserved. What type of forces are involved in elastic collisions? Remember we had two types of forces that we talked about, but you'll need to know the difference between for the test. What are the two types of forces? What's that? No, there were a lot, yeah, conservative and non-conservative. I remember conservative forces conserve energy. Those included field forces like the gravitational force and the electric force, and non-conservative forces don't conserve energy. So when they act, they lose energy. All right, so in this case, which of those are we going to have, conservative or non-conservative forces at play? Conservative, right. So we're going to have forces that do conserve energy. So anytime you have an elastic collision, the forces that will be at play will be conservative forces. That is those field forces, the gravitational force and the electric force. So there aren't many examples of a truly elastic collision. There's really only one that I can think of. Y'all know of collisions between objects that involve field forces? Chemists? What are collisions between objects that involve field forces? That means that the objects will come together and they'll interact with one another, but they never actually collide. They never actually touch. Okay, yeah, magnetic forces. So if you have magnets that come together, they can interact with one another, but they never actually touch. But what's another? Okay, nuclear forces. Yeah. That's not what I'm getting at, though. When we have collision of gas particles. So when gas particles interact with one another in an ideal gas or in a gas period, they don't actually collide with one another, they don't touch, their electric fields will interact and they'll bounce off one another without actually touching. So a good example of an elastic collision is the interactions between gas particles. You'll talk about that in PChem. We can also approximate some collisions as elastic. That is where we have collisions between objects and they just don't lose very much energy. So a good example of this are like billiard balls or pool balls colliding. You're losing some amount of energy, but not very much. So you can approximate them as elastic collisions. And then in inelastic collisions, only momentum is conserved. And energy is not conserved. And these are, all the other collisions. So every collision and every collision between objects, momentum is always conserved. Right. So even if you have two cars that crash into one another, you're losing lots of energy in a car crash because the car crumples up, you lose energy to heat and sound, and but mainly in the deformation of the metal, which takes up a lot of energy. Even in those collisions where you lose a lot of energy, you're still conserving momentum. So you can still describe the momentum as being the same before and the same after, even though you've lost a lot of energy. So inelastic collisions are all other collisions. We also have a special case of inelastic collisions, and those are perfectly inelastic. That just means that after the collision they stick together, right here. So I have two objects that are moving with certain velocities, and then afterwards they move with the same velocity. And I have an example next. It's a quick test question we'll work through. These work out exactly the same way as we had before, the 2D collision problem that we had before, except now V2F is going to be the same for both particles. So it's actually quite a bit easier. Let's try this quick test. I'll give y'all just a minute. So remember, what you're doing here is you want to describe the initial momentum of both particles and set that equal to the final momentum of the particles. But in this case, VF, which you'll find in vector notation, will be the same for both particles. So on your P final, you're going to have M1 plus M2 times your VF. So it's just like the quick test that we did the other day, except you're not going to have two separate V finals. You'll have the same V final for both particles. Let's try this out first. I'll give y'all a minute or so head start. Right, there's only one V final, so both particles move at the same speed and in the same direction. And this type of collision is an inelastic collision, or specifically a perfectly inelastic collision. I'm going to start working it out here as well. Remember, when you're working these, you keep your I and your J separate, and then you'll solve then for a VF I component and a VF J component in the X and Y directions. Anybody have VF yet?
Is it 2/3 I minus 1/3 J?
2/3 I minus 1/3 J. Is that right? Everybody else agree? Yeah. Okay, so let's see. I'm going to go through the algebra here right quick. So I have 8I minus 2J minus 4I equals 6 VF. And now we're solving for VF, but we're going to keep our I's and our J's all separate. I can simplify this a little bit. 4I minus 2J equals 6 VF. And Cole's right to divide both sides by 6. So that's 4 6, which is 2/3 I, minus 2 6, which is 1/3 J. And so that's our final velocity of both particles. Means they're going to move off in what direction? Like in this direction. Okay, that's a perfectly inelastic collision in 2 dimensions. I think these are pretty straightforward, right? I could do this on the test. You'll need to, so make sure that you're okay with it. If you're not, then please practice. I would practice anyway, just to make sure that you're up on what to do. All right, let's finish up the clicker questions, and then I want to work through one other type of problem for for elastic collisions, where we have both energy and momentum conserved. I think we left off with the car. Did we leave off on this one? Did we do this one? No. Okay, so here I have a small car and a large truck. They collide head on and they stick together. Which one has the larger momentum change? Did the car or the truck, they both have the same momentum change, or you can't tell without knowing the final velocities? Now we know from the conservation momentum that the change in momentum is going to be zero, right? That for the system, that my initial will equal the final momentum, or the change in momentum is zero. But which one of these has the larger momentum change then? The car, the truck, the same, or you can't tell without knowing the final velocities? Alright, we're sort of all over the board. I'm going to stop though in about 5 seconds. I'll stop at 120. Let's see. It's like we're sort of split between A and C. Answer C here. They're going to both have the same momentum, change in momentum. A couple different ways that you can think about this. You can think about this that P initial is equal to P final, right? So that means that the change in momentum is equal to 0. So if I think about the total system, if I add up all their changes in momentum, then the total change in momentum will be 0. Okay? So the car will have a change in momentum, and the truck will have a change in momentum, but the total will be 0. So if I imagine then that I have the car with a certain momentum initially, and the truck with a certain momentum initially, those momenta will change, but they're going to change by the same amount, right? So that the total momentum change will be 0. Another way to think about it, which might help a little bit, is that if you think about Newton's third law, they're going to have forces that act on each of these vehicles in the collision, right? How will those forces compare? Will the car exert a larger force on the truck exert a larger force on the car, or will they have the same force, according to Newton's third law? What, Hunter? They're going to have the same force, right? So as these collide, when they come together, they will both feel a force that's equal but opposite, right? How does the time compare for the car and the truck in the collision? They're going to have the same amount of time, right? So the force is going to be the same, the amount of time is going to be the same, and since I know that the force is related to the change in momentum in this way, if the forces acting on the vehicles are the same, the time is the same, then that also means that the change in momentum is the same. All right? Now, one of them will feel a larger acceleration. Which one is that? The car, because it has a smaller mass, and it's going to have the same force acting on it as the truck, but has a much smaller mass, so it'll see a much larger acceleration. We'll see some more like this in just a second. All right, 2 boxes, one heavier than the other, are initially at rest on a horizontal frictionless surface. The same constant force F acts on each one for exactly 1 second. Which box has more momentum after the force acts? Same force, same amount of time. Which block will find it has more momentum after the force acts? Oh, I'm sorry, I lost it there. If you clicked in before, click it again. Okay, doing well. Just a few more seconds. I'll stop at 25. If you clicked in right at the beginning, go ahead and click in again. I unplugged the base by accident. I think that's everybody. Okay, it is C here. I have the same force for the same amount of time. I have the same force acting over the same amount of time, so each one will find the same amount of momentum. Now, which block will be going faster? The lighter one, right. I have a force acting on it on a smaller mass, so it'll see a larger acceleration, and so it will be going faster. Or you can also think about it as, P is equal to mv. They both have the same momentum, so the one with a smaller mass will have a larger velocity. Right, but if I have this force acting for the same amount of time, I'll see the same change in momentum. But they're not going the same speed, but they have the same momentum. I think we already answered this, but which box has the larger velocity after the force acts? Stop at 20. What do you call, or what's the name of a guy with a car on his head? What? No, that's not a name. And then you say, I don't know what. Right, Jack. Get it? Like a jack, like Carter. Okay. A small beanbag and a bouncy rubber ball are dropped from the same height above the floor. They have the same mass. Which one will impart the greater impulse to the floor when it hits? I remember that impulse. We defined this early on. Impulse is equal to force times the change in time. But we also know that the impulse is equal to my change in momentum. So which one will see the larger change in momentum? Or which one will impart the greater force, the greater product of force and change in time? Another way of asking this question, because most of you have it wrong right now, another way of asking this question is which one will hurt worse? Right? I'm asking if I throw a beanbag and I throw a rubber ball, which one will hurt worse? Because the one that imparts the greater impulse is the one that will hurt worse. The beanbag or the rubber ball? We're still sort of mixed bag. I'm gonna help y'all through this. So, if I have a rubber ball and it drops down, it bounces off the floor and comes back up. Right. So this is my initial velocity, and this is my final velocity. So my delta v will equal m. Let's give these some numbers. Let's say this is -2, and this is +2. So it's going to be the final minus the initial, right? Our 4 is our change in velocity. The beanbag, on the other hand, it goes down. Let's say it has an initial velocity equal to -2. And what happens when it hits the floor? It stays there. So it has no rebound, right? It doesn't rebound at all. So the final velocity is equal to 0. So its change in momentum will be m times 0 minus -2. And so it has a much less change in velocity. Now, which one will impart the greater impulse on this? All right, doing pretty well. Just a few more seconds. I'm going to stop at 250. All right, B is the right answer. It sees a greater change in velocity, so it has a greater change in momentum, so it's going to experience the greater impulse, or the greater force times delta T. Have y'all ever, when I was in high school, I went to a boarding school, so I lived in like a boys' dorm for 11th and 12th grade, and we'd make rat tails. You know what a rat tail is? And you take a towel, and if you fold it up just right, you get sort of a handle, and then you get like a little tail. Or if you just pop in with a towel, that works fine too. But a rat tail really hurts. Have you ever been hit with a rat tail? Like, y'all don't do this in women's dorms, right? Hit one another in the butts with towels. Guys like to do this for some reason. I don't understand. But we would take these towels and we'd run around and pop people with them. And they make a lot of noise and they hurt really bad. But what's a good technique for using a rat tail? You gotta whip it. You gotta swing it out there and then you gotta bring it back. And that's the same idea because you get that recoil velocity. And that's what makes it really hurt. Not only when it comes and hits the person, but then you pull it back and you get that recoil velocity just like the rubber ball. The same idea. That's why whenever you hit someone with a rat tail, you gotta like that. Okay? You gotta get it slightly damp, not too wet, but just slightly damp. And then you have to fold it up really tight. Y'all know all about that. But huh? Oh. That's good thinking.
No, you gotta use it tip where it's like the hard part of the towel, like where it's already sewed up.
I can see that y'all giving this a lot more thought than me. All right. A person standing under an umbrella during a rainstorm. Later the rain turns to hail, although the number of drops remains the same, which case requires more force to hold the umbrella. So these raindrops are turning to ice, right? They're not changing mass because you just have these drops become a solid. But which one requires more force to hold the umbrella? Or in which case do the raindrops or the hail impart a greater force to the umbrella? Think about what happens to the raindrops after they hit, and then what happens to the hail after it hits the umbrella. What is the difference in those two? The raindrops and the hail. Just a few more seconds. I'll stop at 1 minute. Still missing somebody out there. All right, good. All right, good job. So why does it require more force to hold the umbrella when it's hail?
Because the hail bounces off back off the umbrella.
The hail bounces off. So for the same reason for the beanbag versus the rubber ball, the hail, when it bounces off, it sees a greater change in momentum, so it imparts a greater force to the umbrella. Plus it's usually windy and bad weather and just whipping it all around. So, it's very controlled thing here. All right, bowling ball and a ping pong ball are rolling towards you with the same momentum. You exert the same force to stop each one, which takes a longer time to bring to rest. The same momentum. Not necessarily the same speed, they have the same momentum. And don't forget that F is equal to our change in momentum over our change in time. I'll stop at 1 minute. Okay, good. Which one's going to be traveling faster? Right, ping pong ball. They have the same momentum, so their product of mass and velocity is the same. But the ping pong ball obviously has a much smaller mass, so it's going to see a larger, a larger velocity. But they have the same momentum, they have the same force acting on them, so they'll require the same amount of time. There's a perfectly inelastic collision. This one block on the left is moving at 10 meters per second. It collides with an identical box. They stick together. What's their final velocity? All right, I'll stop in 1 minute. 1 minute. E is right. This is just a one-dimensional collision. So my initial momentum equals my final momentum. The initial momentum is just m times vi. The final momentum is going to be 2m times vi. 2m because it's m plus m, right? They stick together. Let's see, the m's cancel. 10 meters per second. I'm sorry, this was vf over here. Is equal to 2vf. So vf equals 5 meters per second. A few more of these. I have a uranium nucleus at rest. It undergoes fission. That means it splits apart into two fragments. One fragment is heavy and one is light. Which fragment has the greater momentum? The heavy one, the light one, they have the same momentum, or you just can't say. A few more seconds. I'll stop at 55. 55. Very good. So initially the momentum is what? Of the is 0, right? So initially my momentum equals 0. That means that P1 has to be negative of the momentum of particle 2. They have to add up to equal 0. So they have to be equal but opposite. Which one has the greater speed? Same situation. Which one has the greater speed? The heavy one, the light one, the same speed, or is it impossible to say? I heard somebody's phone vibrating. Did I tell y'all what causes the vibration in your phone? Tungsten. Isn't that interesting? Just a little bitty piece of tungsten. It's so heavy, it just vibrates very well. Or it causes a large vibration. Did y'all tell anybody that little tidbit? You did? It's interesting, isn't it? It's the same thing in your... Huh?
They didn't care, but...
People.
Should have heard my mom laugh when I told her that whole street.
That's useful information. All right. Did you hear about the cat? This is for one of y'all. Did y'all hear about the cat that slid off the roof? It had a small mew. The coefficient of friction. Alright, it's a 1D collision. So as I said on your test, you're dealing with 2D collisions, so make sure you're up on the vector stuff. Stop at 105. Okay, that's right. We know that they're off by a factor of 3, their velocities. They're going to have equal momentum, but one of them is 3 times the mass of the other. So they'll be off by a factor of 3. So Gwen's going to be going slower. Amy, oh, excuse me, I'm sorry. Gwen will be going faster because she has the smaller mass. Amy slides at 6 meters per second, so she's going to slide at 18 meters per second. Looking pretty good. Stop at 55. You might see a simple 1D problem like this in your multiple choice part of the test. Alright, so I can say initially the momentum is 0 because nothing's moving, but then the momentum, you'll have one momentum vector in this direction and one momentum vector in this direction, the cart. This will be the mass of the cannonball, which is 10 kilograms, times its velocity, which is 50 meters per second. And it has to equal then 1,000 kilograms times VF. These have to be equal. Solving that, 500 is 1,000 times 0.5 is our final velocity. So B is the right answer. Did I mark that right? Yeah. Almost done. I think this is the last one. Bullet is fired from a gun. The bullet and the gun have equal and opposite momenta. So whatever momentum your bullet has, the gun has the same momentum. If that's true, why is the bullet deadly, whereas it's safe to hold the gun? Okay, so a few more seconds. Stop at 58. Let's see. Yeah, so it has more kinetic energy. They have the same momentum, but the mass of the bullet is smaller, so it has a bigger velocity. But remember, for kinetic energy, it's proportional to the velocity. What? How is it proportional to velocity, kinetic energy? Right, it's a squared, it's quadratic. So if you increase v, the kinetic energy goes up a lot faster because it's a quadratic relationship. All right, I want to show you a little video. This is just for fun, but it is similar to like the car and the truck colliding. Remember, they feel the same momentum, but which one felt the greater acceleration? The car, because it has a smaller mass, right? So it will accelerate at a much faster rate. So this is a little video a student sent me. I don't think it was anybody in this class. It might have been, but it was with Swiss balls. We call these exercise balls. Those big balls that you sit on or whatever. Pregnant women use them. So, I don't know. My wife always had one when she was pregnant. But these people would grab them in front of them, and then they'd run together and collide. Have y'all ever done this? You gotta try this. Like,
friend today, she got a concussion.
yeah, maybe you don't have to try it, but it's kind of fun to watch. So remember, this is because we have two objects colliding. Now their change in momentum is going to be zero, but especially when you have one person that's a lot smaller than the other, they'll see the same change in momentum, but because they have a smaller mass, they'll see a greater acceleration. So there's also, towards the end of this, we have a collision in 2 dimensions, which is kind of cool.
You ever seen somebody put one on the beach, and like dig a hole in the sand, and then put one of those balls in the sand? It's like a trampoline on steroids, like you go flying.
Really?
It's pretty cool.
I didn't pause this, did I? Oh, shoot. Okay, let's see, where was I? All right. I have one more problem I want to work through. Actually, it looks like we might just do this. Oh, we'll be able to get started on it. Let me show you this other thing. You can do this. Now, if you drop... Where's my ping-pong ball? If you drop a ball, say a basketball, it bounces, right? And you drop a tennis ball, which has a smaller mass than the basketball, it bounces too. And likewise with a ping-pong ball. But if you drop them on top of one another, what happens is, as they go down, they come back up, they bounce up, they feel a change in momentum that's equal to one another, but the tennis ball, which has a smaller mass, will feel a larger velocity. So it's much like the little girl and the little lady and the big guy running into one another, and so they will bounce apart from one another, much in the same way. So watch that, it might come flying out into the crowd. You can do it with a ping pong ball too, like you have these pushing around. But sometimes the ping pong ball will just slide off. So let's just try it. Yeah, it's you can try that out. All right. Are you gonna do the Swiss ball thing? If you like. All right. One more problem. And you don't have any examples like this in your homework, unfortunately. I don't think that you do. Pretty sure you don't. But they're pretty simple. It's really just the working out the algebra. So let's say that I have an elastic collision. And I'm just going to give it some simple numbers just to make the numbers work out. But remember, with elastic collisions, not only is Pi equal to Pf, but also the energy is conserved as well, that my initial energy is equal to my final energy. And that gives you a lot more leeway on what you can solve for as far as the final and initial velocities, because it gives you another set of equations to work with. So let's say that we have two particles that are colliding. Let's say that I have a 1 kilogram particle that's traveling at 2 meters per second. I'll call this V1 initial. This will be M1. And it collides with a particle that has a 2 kilogram mass, and we'll call this M2. And let's say that its initial velocity, V2 initial, is equal to 0. Now normally if this is an inelastic collision where only momentum is conserved, I would need to know at least one of the velocities of one of the final velocities in order to solve for the other final velocity. Because if I don't have that, then I have two unknowns and only one equation. But let's say that I want to know both of their final velocities. So what is v1f and what is v2f? Because this is an elastic collision, I can solve for those because my momentum and my energy are conserved. So it's just like what we've been doing, but now both my momentum and my energy is conserved. So I can say that first, Pi is equal to Pf, our m1 v1i plus m2 v2i is equal to m1 v1f plus m2 v2f. I can also say that the energies are conserved, 1/2 m1 v1i squared plus 1/2 m2 v2i squared equals 1/2 m1 v1f squared plus 1/2 m2 v2f squared. So now I have two equations. I can simplify them a little bit because v1 initial is 0, so that goes to 0 and that goes to 0. So I just get rid of these terms completely. Or excuse me, no, I'm sorry. It was the v2, right? So v2i, thank you, is 0. So I can get rid of these terms completely. But still, I only have two unknowns and two sets of equations. So I can solve that by substituting one equation into the other. I don't think we have time to go through all the algebra. But I'm going to take a couple steps. We'll get you out in just a couple minutes. So if I take this equation and I solve it for v1f, I can get an expression for v1f, and then I can plug that back in up here, and then solve for v2f. So v1f is equal to m1 v1i minus m2 v2f divided by m1. If I put my numbers in there, that's 1 times 2 minus 2 v2f divided by 1, and then I get an expression for v1f in terms of v2f, 2 minus 2 v2f. All right, I take this and I plug it in for v1f, and now I have an expression with only one unknown in it, and I can solve that for v1f. All right, we'll stop there. We'll come back and finish solving this, or if you want over the break you can solve it. But this is exactly the same as what we've been doing, except now instead of just momentum or just energy, they're both conserved. All right, we'll spend some time on Monday finishing this up. We might start on chapter 7, but if y'all have questions or if you want particular things that you want to review on Monday, then please bring those questions. We'll have time in class. All right. But if not, we'll just go on to chapter 7. You have a good break, okay? Good weekend.